Welcome to this next video in the series on acid-base chemistry. In the previous video, linked in the description below, we saw that several types of reactions were possible. For example, a strong acid donating H+, reacting with a strong base donating OH-, will simply produce water. This is called a neutralization reaction and finishes at a pH of 7. A strong acid donating H+, reacting with a weak base, B-, pluses and minuses will attract, and I wind up with the conjugate acid, HB, meaning the equivalence point will be at a pH of less than 7. The third possibility, if one takes any weak acid HA and reacts it with a strong base OH-, the acid will donate an H+ to the OH- to make water, and one is left with A- or the conjugate weak base. This will have an endpoint with a pH of greater than 7. This last reaction was looked at in some detail in the previous video. If one looks at a titration curve for a weak acid, where HA is in equilibrium with H+ and A-, and that weak acid has an equilibrium constant, Ka, of products over reactants, one sees the following. The titration curve, with pH on the y-axis and volume of base on the x-axis, is actually going to be a two-step curve, where, someplace around the midpoint of the reaction, you have a region of zero slope, essentially a region where the pH is constant. This happens for a very important reason. When I am reacting a weak acid and a strong base, the product is the conjugate weak base. So at the midpoint, the moles of weak acid and conjugate weak base are going to be equal. Therefore, the equilibrium constant H plus A minus over HA simply becomes H plus times 1, or at the midpoint of a titration of a weak acid and a strong pH is equal to pKa. If I look at this in more detail, this region of no change in pH is called the buffer region. This can be examined by taking the negative log of the Ka. Negative log of Ka is pKa. Negative log of pH of H+ is pH. And then I have a leftover term of the negative log base 10 of weak base over conjugate weak acid. This is generally written as something called the Henderson-Hasselbalch equation, where the pH is equal to the pKa minus the log of the concentration of weak acid over the conjugate weak base. This equation is worth noting because it describes the behavior of buffers. And buffers are worth learning about because they're essential to life on Earth. Essentially, a buffer is a mixture of a weak acid and its conjugate weak base. Its importance lies in the fact that it allows acid-base reactions to occur at a constant pH. So, looks at a simple thing that's essential for life, such as eating. Metabolism is basically a series of acid-base and redox reactions. The simple fact of eating your food starts with, obviously, chewing it, and then swallowing it. As one swallows the food, it goes down the esophagus and into the stomach. The stomach secretes HCl, but it is also buffered. Therefore, when the food in the stomach is consumed by the HCl, it is turned into nutrients that can be extracted by the intestines. Things would be much different if buffers did not exist and one tried to eat without a buffer. With no buffer, there is no longer anything to protect the stomach, so when the food starts to be digested, that's pretty much the end of everything, and your stomach would wind up with a hole burned through it. So it's plain to see that buffers are useful. Question is, how do you use them? How do buffers work? This can be most easily shown with an example. I'm going to prepare a buffer by dissolving 1.5 grams of sodium acetate, a weak base, NaCH3CO2, in 250 milliliters of 0.1 molar acetic acid, CH3CO2H, which we know is a weak acid because it's not on the list of 6 strong acids. And additionally, we know it's a weak acid because it has an associated acid dissociation constant, an equilibrium constant of 1.8 times 10 to the minus fifth. So, to determine the pH of this buffer, the first thing to realize is that buffer is a key word. And as mentioned, buffers are described by the Henderson-Hasselbalch equation. pH is pKa minus the log of the concentration of weak acid over the concentration of the conjugate weak base. A second thing to note is that concentration is given in moles per liter. However, a buffer is a single solution. The weak acid and its conjugate weak base, in this case, are both dissolved in 250 milliliters of solution. Therefore, the volumes cancel, and the Henderson-Hasselbalch equation becomes pH is equal to pKa minus simply the moles of acid over the moles of conjugate base. For this reaction, I have 1.5 grams of the base, sodium acetate, which weighs 82 grams per mole. So I have 0.018 moles of base. I have 0.25 liters of 0.1 mole per liter of the weak acid acetic acid, or 0.025. So the pH is wind up being the pKa, the negative log of 1.8 times 10 to the minus fifth, minus the log of the moles of acid, 0.025, divided by the moles of base, 0.018, or 4.75 minus the log of 1.42. This buffer has a pH of 4.59. This pH is an intrinsic property of this buffer with this ratio of weak acid and weak base. It doesn't explain how a buffer works. A buffer works by allowing acid-base reactions to occur in a constant pH. So, what would happen to this buffer if I added 10 milliliters of the strong acid, HCl? Once again, HCl is a strong acid which donates H+. It will react with the weak base in the buffer, the acetate ion, CH3CO2-. But the product, as we've seen, of a strong acid and a weak base is going to be the conjugate weak acid, CH3CO2H, or acetic acid. So, if I'm adding 10 milliliters of a 0.5 mole HCl solution, essentially 0.01 liters of 0.5 moles per liter, means I will have added 0.005 moles of H+. If one sets up a table with the conjugate base and the conjugate weak acid, I know initially I had 0.01 moles of base and 0.025 moles of acid. I also know that my strong acid reacts with my weak base, so I will lose 0.005 moles of weak base, but make 0.005 moles of the conjugate weak acid. So at the end of the day, when one does a acid-base reaction in a buffer, the only thing that changes is the ratio of weak acid to weak base. In this case, that ratio changed from 0.025 to 0.018 to a ratio of 0.03 to 0.013, giving a pH of 4.38. Notice The pH did not stay completely constant in the buffer. Initial pH of 4.59 did change to 4.38, so there was a drop of 0.21. However, if one looks at the same reaction in water, in other words, I added 10 milliliters of my half molar HCl to 250 milliliters of water, you will see something stark happening. Assuming I have pure water, I know the initial pH is going to be 7. If I now add my 0.005 moles of H plus to a solution that's now 250 plus 10, or 260 milliliters, I now have a 0.017 molar H plus solution, or a pH of 1.78. This gives a rather large change in pH of 5.22. At this point, it should be noted or remembered that the pH is a logarithmic scale. So a change in pH of 5 means that there's now 100,000 times more acid in the solution than there would be without the buffer. So, in general, this is what buffers do. Buffers allow the conversion of a strong acid into a weak acid, because the strong acid will react with the weak base in the buffer to make the conjugate weak acid. And buffers take strong bases to react with the weak acid and give the conjugate weak base. So essentially, a buffer takes strong and turns it into weak. That is the main power of a buffer and why they are useful. The other reason why they're useful is because, again, they are necessary for life and there are thousands of possible possibilities. Even in a simple experiment with bacteria, every living thing gives off waste products, and those waste products can change the pH of the medium that things are being grown in. This is going to have a deleterious effect on the experiment. In order to properly perform an experiment, pH has to be kept constant, it has to be monitored. So generally, you have to do experiments in a buffer. The nice part about buffers is that they are combinations of weak acids and conjugate weak bases. So, you can pick any known acid and make a buffer out of it. In this case, if you need a buffer with a pH of 7, you find the nearest acid, which has a pKa of close to 7. You then adjust the ratio of acid to base to get the proper pH. So in this case, sodium hydrogen phosphate had a pKa of 7.2. The required pH was 7, meaning the ratio of the weak acid over the conjugate weak base, 10 to the 0.21, would be 4.76 to 1. This will give a buffer with a pH of 7. Key thing to note is that the ratio of HA to A minus is the thing that gives you the pH. However, buffers do not last indefinitely. You can't add an infinite amount of acid and base to buffer. So you now have something called the buffer capacity. We found that a 4.76 to 1 ratio will give a pH of 7. So if I make another buffer with 47.6 moles of acid to 10 moles of weak base, it would have a pH of 7. Or 0.476 to 0.1 would also have a pH of 7. What changes is if the first buffer has a capacity of X, the second buffer would have 10 times more, and the last buffer would have 1/10. So essentially, you adjust the ratio of HA to A minus to achieve the proper pH, and you add more HA and more A minus in the same ratio to increase the capacity. So in summary, When one is faced with a buffer, one immediately goes to the Henderson-Hasselbalch equation to discover the pH, which can be changed by adjusting the ratio of acid to base. It's also possible to create a buffer to meet one's specific needs because there are such a large number of weak acids and weak bases. There's almost an infinite number of combinations and possibilities that exist to get you the pH that is required. Once again, I hope you found this video useful and helpful, and thank you for listening, and enjoy.